Alright, welcome back. Now we're going to see what happens when we have acceleration going in an upward direction. In other words, analogous to liftoff with the rocket. You have to watch very quickly. It's going to happen very, very fast, and I might even see if I can capture this and slow it down and place it somewhere on the screen. So here I am, stationary. Now watch the needle very carefully as I lift upwards. Which way does it go? Ready? Very quick. I'll do it again. I'll start a bit lower. Hopefully you should have noticed it deflected downwards, indicating that we had more apparent weight. Here I'll do it in slow motion. Ready? There you go. See? Slow motion. So when I went upwards, the needle deflected downwards, indicating that there was more weight. So the apparent weight of the system, or of this, increased when there was acceleration. Let's see if we can prove that with a little bit of maths. So remember before we had the tension force going up, and we said that we had this way was being positive, this way was being negative, because in actual fact we were accelerating. We're accelerating. I was pulling upwards. So we're going to be saying that up is positive according to this, our definitions here. We had a force going downwards. We had our gravitation going down. Okay, so if we looked at what we did before, our sum of F net in the y direction, we said before was we had the force going up, so we had our tension force plus our gravitational force. It was going down, gravitational force, so therefore we have to give it a minus like before, exactly the same. And remember we said that the tension force, so this was actually measuring the weight or the apparent weight, so let's just put W there for weight, minus mg. But in this instance here, because I was accelerating, the sum of the forces was not zero anymore. I was applying a force, and we know that the applied force, right, is equal to ma, right, mass times acceleration. So let's write that in, ma, and it's going upwards, so it's positive, so we have positive ma here. What does that mean? Well, we do a bit of rearranging. It means our weight, our apparent weight that was being measured by the scales, was equal to ma plus mg. Okay, so our apparent weight has gone up now. We can see that it's got our mg, which is our normal weight, plus the applied force ma. So this is our apparent weight. So therefore g force, if you wanted to calculate that out, would be the apparent weight divided by the true weight. And this, the apparent weight was that, ma plus mg, divided by the true weight, which is mg. And if we wanted to take m out as a factor, it would be a plus g over mg. Okay, and I can even cancel the m's now. So this would be equal to a plus g over g. So in other words, your apparent weight is normal g experiences at ground level plus your acceleration. So in other words, therefore, g is greater than 1, right? Now, depending upon how fast you're accelerating, will depend whether you like your 2g, 3g, 4g, etc. So that was for the scale, and we saw that with the scale, it increased and got a larger value. And the same thing would be happening if we were looking at a rocket. Exactly the same, right? So let's do a rocket. So here we go. And of course we have our little astronaut in their seat. And we have Fg coming down, force of gravity. We have the normal force going up that's equal, but then of course we've got the applied force from the thrust, right? So the thrust is supplying the applied force, and we have exactly the same thing. So we have F net, hopefully you can see over here, is equal to the normal force plus the gravitational force going down But remember, F net, just like over there, is not 0. It's actually ma. So normal force, whoops, minus mg. So the normal force that you experience, on your chair inside the capsule would be ma plus mg, right? Therefore, the g force that you experience would be that over mg, just like we have over here, and it does the same, right? Acceleration, oops, didn't put that there before. Acceleration plus g over g, and that's going to be greater than 1. All right, so hopefully that makes a bit more sense, that when you're down on the ground, you're not moving, you are therefore experiencing 1g. When you're accelerating, your apparent force increases, therefore g is greater than 1. But what about when you are up and you're orbiting? Let's consider that next quickly, because the video is getting fairly long. As you can tell by my extremely detailed diagram there of the astronaut sitting in his chair, we're going to be talking about weightless or 0g. Now, a lot of people get confused about 0g because they think that they are weightless, they have no weight. Well, they do have weight, you just don't have apparent weight. Because, see, there is g, there is gravitational force that you experience when you're in orbit. I mean, there is gravity there because, I mean, how does the Earth keep going around the moon? There is a gravitational acceleration, centripetal acceleration that pulls the moon, right, inwards, and therefore gives it its orbital path around the Earth. So gravity extends outwards. The reason why you feel weightless, however, is your apparent weight. Remember, we said apparent weight is the weight that you feel, and especially when you are pushing against an object. So, under normal circumstances, on the ground here, you'll have Fg, I should say mg like that, and then you'll have the force, the normal force going upwards on you, and it's that normal force acting on you that you feel like you have a certain weight. However, when you are in orbit, both you and the chair are falling or accelerating backwards towards Earth. Right? Both of you have gravity acting on you, and there's no normal force from the chair pushing up against you, and therefore you feel like you're weightless because you don't have that apparent force that you feel. It's 0. Right? So both of you and the chair are falling. It's exactly the same if you were falling in an elevator. Both you and the elevator are falling at the same rate, and there is no normal force pushing up against you, and so therefore you feel weightless. In fact, this apparent force is around us a lot of the time and gives us false readings. For example, you might be, when you're on a ride at a amusement park, you're going around and around and around and around, right? So let's just try and draw that from the top view. There's you. And there's the center of the ride, and so you're going around like that. And there used to be a force that people used to say, the centrifugal force, an outward-seeking force that would go outwards, and that you would have that force, and that's what you felt. However, that is an apparent force. It's not a true force. It's apparent. Because what's actually happening here is Newton's first law. Newton's first law says you want to keep going on in a straight line, right? However, as you're turning around, you're being pulled inwards by the centripetal force. The centripetal force is pulling you in and therefore changing your direction and causing you to accelerate. And it's the force that you feel against the floor or the seat or whatever it might be that gives you that feeling that you are being pushed against the wall of the seat, etc. That's called the apparent force or the centrifugal force. Okay, you experience it on buses when you go around the corner. Okay, you want to go in a straight line, but the bus is turning that way, and therefore you're being pushed. Your motion, your direction of motion has been changed. So that's an apparent force. And so here in weightlessness, your apparent force is not apparent because you're not touching anything. You're not having got this normal force. So both you and the object, the spacecraft, are falling down at the same rate, and so therefore you appear weightless. Okay, and we call that 0G. So that's it. Okay, hopefully G-force makes a lot more meaning for you now, and I'll see you in the next video. Keep doing your physics and having fun.